going to assume that G is a finite permutation group acting on some finite set omega that has at least 2 points, so we're not trivial action. I'll always assume that G is transitive, and whenever I mention a group H, I'm assuming it's a point stabilizer of G. And so in particular, we're interested in looking at the actions of G on the right cosets of H. Okay, so in order to say anything about almost elusive groups, I first need to discuss derangements, which is something that Cheryl Prager mentioned earlier. So what's a derangement? What we've already seen. It's an element of my group that fixes no points, and this is equivalent to saying that the conjugacy class of this element inside of G does not intersect my point stabilizer. And we can give these set of derangements notation and call them delta G. Okay, so what can we actually say about this set of derangements? Well, the first important thing to note is that actually the number of fixed points of an element is fixed under conjugation, and so in particular I can write my set of derangements as a union of conjugacy classes, and so what I want to take away from that to define almost elusive groups is the fact that thinking about conjugacy classes of derangements is a very natural thing to do. Okay, but we could also ask, when do I actually get existence of a derangement? As we've already seen, there always exists a derangement inside my group, and this was proved by Jourdain in 1872, so it's a very old theorem, and it's proved using really basic group theoretic concepts like the orbit counting lemma. Now we have existence, we can also ask lots of other questions. In particular, we could ask, what if I also required that my derangements have other properties to them? For example, if I want my derangement to have prime power order, when do they exist? Quite a restricted property, and it turns out that actually there always exists a derangement of prime power order, and this was proved by Affine, Cantor, and Schacker in 1981. And the proof of this uses the classification of finite simple groups. So we can already see that just going from proof of existence to proof of existence with a restrictive property, the proof becomes a lot harder. Okay, but we're group theorists, we like to push it as far as we can. Can I remove the power condition? Does the same thing hold? Do I get derangements of prime order inside of my group? Unfortunately, this is where it fails. So there do exist groups that do not contain a derangement of prime order, and we call these groups elusive. So the nicest example I can give is the Mathia 11 group with its action on the right coset of PSL211. This is elusive. It's actually not too difficult to show why, but I won't because of time restrictions. Okay, again, group theorists, we like to classify things. Can we classify the transitive elusive groups? Unfortunately, this is an incredibly difficult question, but we can ask the question for slightly smaller classes of groups, namely the primitive groups, which we've seen many times today. And in 2003, Giudice classified all primitive elusive groups, and it turns out that actually this example is the only example of a primitive elusive group. Giudice actually classified a slightly larger class of groups, but for the purposes of this talk, we're solely interested in thinking about primitive groups. Okay, so at this point, you're probably wondering what is an almost elusive group. And elusive groups and this idea of conjugation gives really good motivation to what is an almost elusive group. So we say a group is almost elusive if it contains a unique conjugacy class of derangements of prime order. So now I'm allowing the existence of these derangements of prime order, but I'm putting restrictions on them by requiring a unique conjugacy class. So very nice example, take n to be a prime power, take Sn with its natural action on endpoints, then this is almost elusive. So if I'm going to have a derangement of prime order in Sn, then it has to be of order p because the prime must divide the degree. And obviously we know then if it's going to be a derangement, it can't have any one cycles, so it's literally just p cycles. But this means I have a unique cycle shape and thus a unique conjugacy class. Okay, so again, we want to ask this question, can we classify them? And again, classifying the almost elusive groups for the entirety of transitive groups is actually incredibly difficult. So what we want to do is reduce down to these primitive groups again. So we're now going to assume for the rest of the talk that this group is primitive. And in particular, as been stated many times before, it just means that I'm assuming that my point stabilizer is a maximal subgroup. Okay, and again, as we've seen many times before, the nice thing about primitive groups is the Onan-Scott theorem. So I can partition these groups into 5 different families. And what I want to do really with this kind of almost elusive case is to, in some sense, reduce the families that I exist inside of, and see if we can say anything about that. So this is joint work with my supervisor, Tim Van-Ness, and we managed to prove that if you take a primitive almost elusive permutation group, then the group belongs to one of 2 of those 5 families. So it's either almost simple, or it's an affine group, and in particular in the affine case, you also require that it's two-transitive, which I'll explain a little bit later why that comes about. Okay, so again, we've seen most of these definitions multiple times, but we say it's almost simple if it's contained between a non-abelian simple group and the automorphism group of that non-abelian simple group, and this non-abelian simple group is called the socle. And then in an affine case, I'm taking a vector space over a field prime characteristic, and here I guess the really important thing to take away is this fact that we can write G as a semi-direct product. So really I can write my elements in my group as kind of a pair of elements, one inside of the vector space and one inside of this point stabilizer, which is a subgroup of GLDP. And G is acting on the vector space via affine transformations. Okay, so we've reduced down to almost simple and affine, and so now it's kind of, in a very simplified way, it's just going into these families and seeing what we can say. And actually, I managed to classify all primitive, almost elusive groups up to isomorphism. So obviously, I'm not going to provide the tables because they're quite big, but I'll give a couple of examples. So we've already seen the symmetric group with its natural action. Now let's look at the symmetric group with its action on the set of two sets. And for this to be almost elusive, we require that either n is a Fermat prime or n-1 is a Mersenne prime. Another example, so take the group to be the projective general linear group, PGL2Q. Take our point stabilizer to be of type P1, so this means it's the stabilizer of a one-dimensional subspace of the natural module. And for this to be almost elusive, we require that, firstly, Q is prime, but in particular has to be a Mersenne prime. And then finally, an affine example, so here we're taking just sort of any old prime, any D, the vector space FPD, and then the point stabilizer here is GL1PD. So what I really want to take away, I guess, from this is the fact that it's very common in the almost simple case to get quite heavy number theoretic restrictions on the cases, and it's less common inside of the affine groups. For example, here we obviously have some kind of doubly infinite case where P and D could be anything. Okay, so sort of the remainder of my talk is just going to be some kind of explanation as to the techniques that we used in order to get this classification. So firstly, we'll look at the almost simple groups. So assume it's a primitive almost simple group with socle G0, so this is this non-abelian finite simple group, and point stabilizer H. Then there are two sort of facts that make we use for some form of reduction. So firstly, we remember this sort of alternative way of defining a derangement. So X is a derangement if and only if the conjugacy class of X and G does not intersect our point stabilizer. And secondly, the socle is a normal subgroup of my group, and so in particular, if I take an element in the socle, then the entire conjugacy class is contained inside the socle. And so if we combine these two facts together, we get this kind of secondary reduction that G is almost elusive if and only if this pi G0 minus pi H0 is less than H1. So H0 is the elements of my socle that live inside of my point stabilizer, and this pi of X just denotes the number of prime divisors of the order of X. So this is nice and easy to see, because if I take a prime that divides the order of G0 but doesn't divide the order of H0, then because of these two, a combination of these two facts, every single element inside of G0 of that prime order is a derangement. And so if I have two unique primes that satisfy this, I obviously have two distinct conjugacy classes of derangements. So this is kind of, we obviously have alternating, sporadic, and groups of Lie type to kind of consider. So for the alternating and sporadic, this is sort of working its way in the background, but initially our approach wasn't to sort of use this fact outright. But where this came in amazing handy was for the groups of Lie type, because obviously there are many, many groups of Lie type and many, many maximum subgroups. And so a reduction for this was very useful. So I proved, so suppose that G0 is a group of Lie type and the condition holds, then this belongs to a known list of cases. So actually the cases in which we get equality were proved by Liebeck, Prager, and Saxel, and so this is kind of an extension of that result in this particular case. And so once we kind of have this reduction to these cases, then it's sort of a question of just running through those rather than running through every single case that we have. Okay, so what about the affine groups? So take G to be a two-transitive affine group. Our socle here is this vector space, obviously with a group structure on it. Our point stabilizer is contained inside G or dp, and we're recalling again that we have this nice kind of structure to it, so we can kind of write our elements as pair. So what does it actually mean to be a derangement of prime order inside of this group? Well, firstly, if it's going to be a derangement of prime order, the order must divide the degree, and so we must be of order p. And so we can now ask, well, what does it mean to be a derangement of order p? So we'll take this pair of elements, and it's a derangement of order p if and only if the following holds. So H is either trivial or of order p, V is contained inside the kernel of this map, and V is not contained inside the image of this map. So this bottom condition is required to be a derangement, and the top two are required to be an element of order p. And so now we can immediately see that if I took V to be non-trivial and H to be trivial, everything satisfies this. And so I know that every single non-trivial element in my vector space is in fact a derangement of order p, but this is precisely what it means to be two-transitive. So this is where this two-transitivity condition comes from, the fact that we know that all of the non-zero vectors are in fact derangements of prime order. So just as I said that. And additionally, if we took V to be trivial and H to be non-trivial, this means they live inside the point stabilizer, which means I know they're not derangements. And so what we're now interested in doing is looking at the cases where V is non-trivial and H is non-trivial, and asking, can we find a derangement of order P or not? And if we can't find one, we know our group is almost elusive. And so to do this, we use Herring's theorem, which classifies the two transitive affine groups. And then it was a lot of what is the Jordan normal form on the vector space of elements of order P inside of our H. And my final result is this kind of lemma, which kind of partially classifies, I guess, in some sense. So take a two-transitive affine permutation group of degree P to the D, then it's almost elusive if and only if one of the following holds. So either P doesn't divide H, in which case I'm obviously never going to find this like non-trivial H, or H and D are both divisible by P, and every single element of order P in H has this particular Jordan form on my vector space. And so now it's a question of kind of reducing to this case and then proving lots of things about what the Jordan form of certain elements look like on our vector space. And that's all I have for today. Thank you.